Okay, let's apply what we just learned to a triangle wave. A triangle wave is one where it's a periodic function where the sort of signal looks like a triangle. Okay, that's what. And can you believe that's why they call it a triangle wave? Okay, anyway, so the mathematical formulation of this, yeah, is the following. Let's look at f of t equal to the absolute value of t. Now, I know you know what this thing looks like. It looks like, its graph looks like this. Maybe I'll draw it over here, just for reference. Its graph looks like a V, like this. Okay, it looks like a V, and it keeps going, okay? But if I imagine that this is -1 here, and this is 1, what we could do is take this picture and repeat it every 2 units. So I could keep going like this. So it's over here, it's like this, and then over here, it's like that, or something like that. Yeah, and it just keeps repeating, you understand? Something like this, okay? That's called the triangle wave. I think that's what it's called. Okay, now, the way that we're going to discuss it, we're going to take this on the interval from -1 to 1 and extend periodically. This is the sort of way we're going to talk about constructing the triangle wave. Extend periodically. And you might worry, oh my gosh, does that mean I have to think about what the formula is for this triangle wave outside of this interval from -1 to 1? And the answer is no. You only ever have to think about what's happening between -1 and 1, at least if we're concerned with finding the Fourier series, which is what we're concerned about here. And what I want you to notice is that this is a 2L, I'm sorry, I said 2L, but it's really a 2 periodic function. So meaning that it's 2L periodic, where L here is 1. So in all of our formulas, it's going to be nice because L is going to be 1. And you can see L makes an appearance in quite a few of these formulas. And we don't need to worry about a complicated L. L is 1. Okay, so it's quite straightforward. Nice. Okay, so now we just got to get to cooking. Okay. Well, important. Let's think about this triangle wave. The first thing that I want you to observe is that this triangle wave has symmetry. It is symmetric about the y-axis in this case, the vertical axis. If you reflect the triangle wave across that vertical axis, it lands on top of itself. In other words, this thing is even. Note, f of t is even. Okay? That's going to be very, very important because it's going to make our computations a lot simpler. Okay? In particular, I'll give you the punchline right away so you don't have to stress about it. Let's look at b sub n. Let's do b sub n first. I know a sub 0 and a sub n usually come first because they are prior in the alphabet, but we're going to go reverse lexicographically now in computing these indices. Is that true? Kinda. Just, we're going to do b sub n first. Stop being a nerd about it, okay? B sub n is equal to 1 over L, that's 1 over 1, times the integral from -1 to 1 of, I just look here, f of t times sine of n pi over L times t. Now, L is 1, so this is just sine of n pi t dt. L is 1, don't forget, L is 1. So this is the integral I have to mess with. Nobody bothers to write that one. I did it for you, but I'm going to erase it because it looks ugly. And so now we have to deal with this integral. Here's the thing about this integral. This one here, that guy, that's even. That's an even function. And this one here, sine of n pi over t, that's odd. That's an odd function. So the product of even and odd, as we've discussed, is odd. We're integrating an odd function over a symmetric interval. So guess what we get to conclude? B sub n is 0 for all n. All of them. They're all 0. So our Fourier series is only going to have cosine terms inside of it. Okay, awesome. That's great. We do have to compute those Fourier coefficients, though. Okay? All right. And let's do it. So let's start with let's do it in blue. I like blue. Makes me feel, yeah, happy. So A naught, the formula, if you can't remember, here it is right here. So we're going to write 1 over 1, which is 1, and I'm not going to write to 1 because that's humiliating, times the integral from -1 to 1 of f of t, which is the absolute value of t, dt. Now, I don't want you to think very hard about this. I mean, in principle, what you're going to have to do, because the absolute value of t is naturally a piecewise defined function, is write this as the sum of two integrals. -1 to 0 of the absolute value of t dt, plus the integral from 0 to 1 of the absolute value of t dt. And what you know, or I hope you know, is that on the interval from -1 to 0, the absolute value of t is in fact equal to -t. So this is equal to the integral from -1 to 0 of -t dt plus the integral from 0 to 1 of, what is the absolute value of t? If t is non-negative, it's just t dt. Okay? My experience has told me that this step right here of going from the absolute value of t here to -t when t is negative is deeply confusing for students. So make sure that you understand that, and don't let yourself fall asleep keeping track of negative signs. Really think through, bust your brain, figure it out. Look at the graph. You see that? That's got slope -1. That looks like -t to me. Okay. Good. And, right. Look what we can do. This is equal to the integral. I'm going to pull the negative sign out. Do I mean it? I don't know. Well, okay. You know what? This is all too much bother. Geometry. Geometry is our friend here. Okay? Because please observe, what we are doing is computing the area underneath this curve, the signed area, between the triangle wave and the interval from -1 to 1. These are isosceles triangles. They're my favorite. I don't know how you feel about them, but they're great. They're easy to understand. They have edge lengths 1, okay? Each of them has area 1/2. So what is this integral equal to? It's equal to 1/2 plus 1/2, which is 1. That's geometry, okay? I don't need to do all of this calculus nonsense. I can just use my eyeballs and my geometric brain balls and figure that out, okay? There it is, 1. That's A naught. If you want to go through the pains of earning that through the integration calculation, you please go right ahead and do it. Enjoy yourself. I'm going to be maxing and relaxing, computing a sub n while you're still drooling over those integrals there, okay? A sub n is given by the integral from -1 to 1 of the absolute value of t times the cosine of n pi t dt. And yeah, we're going to have to think about this one. So notice that this is even and this is even. They're both even functions. The product of even functions is again even. So that admits a kind of symmetry argument which allows us to simplify a little bit this integral over this symmetric interval. The absolute value, how? Well, it turns out that this is equal to 2 times the integral over just half of the symmetric interval from 0 to 1, let's say, of the absolute value of t times cosine n pi t. That's the idea. That because we're symmetric about the vertical axis, and we're integrating over a symmetric interval, we only need to take half of it and then multiply the result by 2 to obtain this integral. Make sure you understand that, because it's going to save you quite a lot of computation, particularly here, because notice that the absolute value of t is pretty nice on this interval from 0 to 1. It is in particular just equal to t. This is equal to, in other words, 2 times the integral from 0 to 1 of t cosine n pi t. How does that make you feel? No, right, you can't answer, but you get it, right? How are we going to attack and kill this integral? I can hear you all saying it at once. Very good. Really good job. You recognized right away. Integration by parts, of course. Duh. That was rude. Integration by parts is how you're going to do it. You're going to let u equal t. Can I do the scratch work up here? We're going to let u equal t, and we'll let dv be cosine n pi over t. N pi times t. N pi t dt. I'm having issues. Look at that. Okay, great. And then I can put my dt in there. Then du is dt, and v is 1 over n pi. Remember, n is not 0 here, so 1 over n pi sine n pi t. Do you believe it? Yeah. If you ever need a check on yourself, remember, just take the derivative of that and you'll get it. All right, so by integration by parts, oh, sure, purple is great. By integration, no, it's got to be blue. By integration by parts, this is equal to 2 times, big old bracket, u times v, so that's t over n pi times sine of n pi t this is evaluated from 0 to 1 minus the integral from 0 to 1 of v du. So that's 1 over n pi times sine of n pi t dt. And then close the bracket, and yeah, we're good. Okay, let's keep going. So first of all, when I plug in 1, notice I've got signs happening here. Sign of integer multiples of pi. And if I plug in an integer like 1 or 0 into that, I'm going to get 0, because sine of any integer multiple of pi is 0. So in other words, this whole bit just goes away. I don't even have to think about it. Great. So what I'm left with is the other bit. And I can't forget my 2. Maybe I'll take out the, can I take out the 1 over n pi, move the 2 in, so 2 over n pi, and I haven't forgotten my negative sign, because good hygiene around negative signs. And I got, what is an antiderivative for sine of n pi t? I think that would be negative cosine. No, I want my coefficient out front. Negative 1 over n pi times the cosine of n pi t. And this gets evaluated from 0 to 1. And again, think about the what's happening here. It looks good. Looks real good. We move that negative 1 over n pi out right away, because we like marrying negative signs, okay, at least while that's legal. That gives us 2 over n squared pi squared. Neat. And then we have here cosine of n pi, oh wow, minus cosine of 0. Okay, this merits attention because this is the same thing as 2 over n squared pi squared times, so cosine n pi we've talked about. Cosine of n times pi, think about when n is odd, we're on the, if you think about angles in the unit circle, if n is even, like 0, 2, 4, 6, 8, etc., then we're at the sort of eastern point of the unit circle, in which case the cosine is 1. But if we're on, for odd values of n, like 1, 3, 5, 7, 9, 11, 13, etc., then we're on the western compass point of the unit circle. And the cosine is -1 there. Okay? And if you think carefully, that ends up being -1 to the n. -1 to the n. Okay. And then cosine of 0 is 1. Okay. -1. Oh, weird. I think this is right so far. And now, can we... Okay, now think about n as n does its thing, as it runs through the positive integers. Again, when n is odd, let's think about n odd first. If n is odd, -1 to the n is -1. And -1 minus 1 is -2. So this is equal to -4 over n squared pi squared if n is odd. Okay? That's what it's equal to there. But what happens if n is even? If n is even, -1 to the n is 1. And 1 minus 1 is 0, I heard. So this is equal to 0 if n is even. So we get this sort of result like this, where we get different formulas for the Fourier coefficient depending on whether n is odd or even. Okay. So what I'm saying is that if we want to write down the Fourier series, so I forgot, what was A naught again? It was 1. That's good. Oh, what was B's? They were all 0. That's great. All right, we didn't have to do any computation there. And the A sub n's for n greater than 1, greater than 0, are given by depending on whether n is odd or even this. Okay, so the Fourier series then. How can we write it all out? So I forgot what it was. Oh yeah, it was the absolute value of t is equal to A naught over 2. So that's 1/2. A naught is 1. So A naught over 2 is 1/2. Plus the sum. Now the sum, B sub n is all 0. The sum is only going to happen for n odd. So maybe I'll write it like this, can I? N odd of A sub n, which is -4 over n squared pi squared, times, now we write the cosine. The cosine of n pi t, right? Because L is 1. I'm looking back at these formulas here. Cosine of n pi t, cosine of n pi t, because L is 1. L is 1 here. So it's going to be cosine of n pi t. Yes. This is what it's equal to. So if I write out the first few terms, I get 1/2 plus, when n is, so I'm summing over n odd. So the first term is going to be -4 over pi squared when n is 1 times cosine of pi t. The next term will be 4 over 2 squared, which is, maybe I'll write it as 4 over 4 squared. 4 over 4, not 4 squared, 4 over 4 pi squared times cosine of, oh my god, I'm losing my mind. N is odd. N is odd. So this is actually 9. N is actually 3. N is 9. 3 pi t. That's the next term. Minus 4 over 25 pi squared cosine of 5 pi t, etc. And it keeps going like this. Okay? And what I'm realizing now that I'm doing this, and I forgot that this was a thing because I have a terrible, terrible memory, but this is the truth. It turns out that you can solve a very famous problem called the Basel problem using this result. But I wonder if that's worthwhile to do. This was a problem that obsessed mathematicians back in the 18th century. And I think the person first credited with solving it, oh, what is it? The Basel problem. I think Basel was a town in Germany or Switzerland or Prussia or something, okay? The Basel problem was about summing up from n equals 1 to infinity the reciprocal of the squares. This is equal to 1 plus 1/4 plus 1/9 plus 1/25 plus 1 over 36, etc. And it took a lot of work by the yellow bag head hat guy, Euler, lazy eye guy, Euler, blue jacket, black stripes, Euler, to compute that this was in fact equal to pi squared over 6. Now, what should blow your mind is like, what in the world does pi have to do with a sum like this, right? Why does pi enter into the picture when computing a sum like this? Because this is the sum of integers. And this is one of those great mathematical facts that generate tremendous amount of ideas and theory and a bunch of just really inspirational result. I can barely talk because I'm just filled with such emotion when I think about the Basel problem. Okay. What I think I'll do, and I claim, this is a big claim, that you can solve the Basel problem using this representation of the Fourier series for the absolute value of t. But maybe that's not directly relevant. So I think what I'm going to do, I'm going to stop this video. I'm going to do another video which is relevant to your life. And then I'll do a bonus video, because I can't resist, in which I solve the Basel problem using this Fourier series. Okay? Okay. Bye.